Hi, I don't know who I'm talking to, but welcome to this session. My name is Yi Chu. I am a graduate student at Penn State University, and today I hope to take you on this journey through my research about how neutrino flavor transformations can reshape our understanding of neutron star mergers, heavy element production, and the signals we can detect. To begin with, I want you to imagine that there are two neutron stars. Neutron stars are objects that are more massive than our sun, but packed into the size of a city. So if you were to have two neutron stars put together at a very close distance, they will orbit toward each other, and at some point they will merge. So let's look at this animation. So you see these two neutron stars, they are moving toward each other, and at the same time, they are pulled closer and closer due to the laws of gravity, and they will eventually merge and unleash a burst of neutrinos and various types of materials. So this is really the event that we're looking at, the so-called neutron star merger. So the first gravitational wave event that was detecting for binary neutron star merger is this GW17-17. So in that event, we not only detected gravitational waves, but also the follow-up electromagnetic counterparts. So the counterparts are including short gamma ray burst and the kilonova light curves. Unfortunately, we didn't see any neutrinos, but this is really the first multi-master astronomy event that we see with gravitational waves. And to understand the neutron star merger process, we need better theoretical modeling. So to understand the merger process properly, we need to break things down into different parts. First, I will talk about the merger modeling, and then I will move on to talk about the neutrino flavor transformations, and eventually I will combine both of them and show what kind of results I'm getting. Okay, first of all, let's talk about numerical relativity. So what is numerical relativity and how do we actually study this? Numerical relativity is basically solving Einstein equation numerically. So here we have Einstein equation in matter space. So on the left-hand side, you have the space-time evolution. On the right-hand side, you have the matter evolution. And the matter evolution is generally what we call as hydrodynamics. But that's not the only part, because there are also neutrino transport that take care of the radiation. So neutrinos can not only help to cool the disk or power the outflow and jets, it can also help with the electronization of the materials. So here, it really comes down to this T mu Newton on the radiation part, and that has to be taken into account into our full T mu nu that has also the fluid part. The way we thought of deal with this T mu Newton for the radiation is by using this classical M1 neutrino transport. So neutrino M1 transport basically decompose the stress energy tensor into different moments on angular space. First, zeroth order moment is this energy, and you have the first order moment being the flux, and then you have to use some analytical closure to relate them to the pressure tensor here. So essentially what we are evolving in the system is this number density, energy, and fluxes of neutrinos, and then on 4 different neutrino flavors. The reason why we use 4 is because here we don't distinguish the mu and tau neutrinos as we don't have mu and tau interactions currently available in the simulation. That also makes sense because the energy scale for these neutrinos to be interacting with the mu and tau will be very high, and then it's typically in a very deep core of the neutron stars. Okay, so now that we finished talking about the theoretical basis, it's really there are a lot of technical details that I skip, but basically to give you a sense of what we are talking about, I want to show you this animation of 2 different simulations of neutron star mergers. So these are just using the formalism we talked about. We have the radiation, we have the hydrodynamics, and we have the spacetime evolution. But here, the difference between the two animation is the equation of state. The equation of state is basically the quantity that, or like a relation that defines how the matter would behave in high density. So we have equal mass neutron star mergers, and they will have initial separation of 45 kilometers. You see this merger happen at different time because different equation of state give you different kind of mobility. And also what's interesting is you actually ended up with different remnant style for different simulations. So the first one, DD2, leads to a longer-lived neutron star remnant, while the right-hand side, SFHO, gives you a black hole formation because of the pressure cannot sustain its gravitational force. Okay, so now that we finished talking about the classical picture of how neutrinos can propagate and then be included in the merger simulations, let's talk about the quantum effect, which is the flavor conversion effects. Before I move on to talk about the theories, I want to give you a brief idea of what kind of impact flavor conversions can bring into the system. So here I'm showing you all these plots I took from previous studies. They are mostly studying on the accretion disk systems, so it's not really the merger phase. But still, you see here the electron fraction, nuclear synthesis, and kilonova light curves from left to right. So the first on leftist column, you have this electron fraction giving you the number of electrons over the number of baryons. So this quantity you see in the upper panel, the flavor conversion case, is lower than the bottom panel non-flavor conversion case. That means your flavor conversion change electron fraction and actually reduce it. Reducing electron fraction also means an increase in neutron richness. The reason why that's the case is because the baryons are proton plus neutrons, and if you have the same amount of electron and protons, that's our assumption, you end up reduce electron fraction means you have increased neutron richness. So if you have an increased neutron richness, what you actually ended up with was a boost in the rapid neutron capture process, and that gives you more heavy element production for the middle column. And a change in the heavy element productions also give you eventually a change in the kilonova light curves that you would expect. Okay, so now that we know what kind of impact flavor conversion can bring to the system, let's see how they actually get into the system. So the flavor conversions we consider are of generally three types: vacuum oscillation, the MSW matter effect, and the neutrino self-interaction. And self-interaction is really the term that gives us this nonlinearity in the flavor conversions, and I'll talk about it later. First of all, here we have this quantity kinetics. Basically, it's a Boltzmann equation in general relativistic form. And what we are evolving here is this density matrix. And since we have 4 neutrino species, basically it's a 2x2 matrix. And then you have these all diagonal terms giving you flavor conversion, and the diagonal terms give you the distribution function for different flavors of neutrinos. One thing you will notice when we actually think about this neutrino self-interaction term is the fast timescale that it has. So when talking about fast, it really, what I mean is nanosecond timescale. And to illustrate that even more, so here we have different plots. If you look at the left top plot, this one is analysis done on neutron star merger remnant, and they found that this flavor conversion growth rate, or this instability growth rate, can be to the order of fractions of nanoseconds. However, as I'm plotting on the right here, when we estimate the hydrodynamical time steps, usually the system will have tens or hundreds, even thousands of these nanoseconds to be the hydrodynamical evolution. So that means if you were to include flavor conversion directly in your system with hydrodynamics, it's really unfeasible computationally because you cannot really deal with these 3 orders of magnitude timescale differences. So this is really the scale separation problem that we ended up proposing this subgrid model to solve. So the solution is this BGK subgrid model, where you treat this commutator term that we have seen on the previous slide by this relaxation process. The relaxation term, or the subgrid term, will assume a given relaxation time tau and a mixing equilibrium state Fa. So with these 2 terms, you basically say that, okay, so I don't know what happens in nanosecond timescale, but I can approximate that by a relaxation process of 1 state going to equilibrium state. And that happens with a given short timescale. Okay, so with that model in mind, we can then think about flavor mixing treatments we can propose. So there are a big table of these treatments that was included in the paper, but basically there are 4 different types. So we need, again, 2 input. First is relaxation time, and mostly we use this 0.5 nanosecond. Second, we need this equilibrium states, and we have different prescriptions for that, which now I'm not going to talk in details. But basically, they will try to conserve the lepton number and electron lepton numbers. So the 4 models we consider here are row 11, row 13, FFI, and this NM stands for no mixing. So the first 3 models are neutrino mixing models. They mix with different density threshold. And the third one is adding an additional criterion being FFI unstable criterion, which I will talk about later. But basically, these are all the models we consider, and we consider them under different equation of state and different resolution. Okay, so now we have the 2 pieces of theoretical modeling. We can then move on to talk about the results that we get when adding neutrino flavor conversions into the system. The first thing that we look at is this general dynamics by taking static snapshots of the simulations on different planes. The first 2 columns are drawn for the XY plane for row 11 against the no mixing, so flavor conversion versus no flavor conversion. And for the third and fourth column, we have then plotted on XZ plane. And we have on different rows the YE, rest mass density, the NUE and NUX. So here you can see that with flavor conversion, you basically have lower electron fraction, similar rest mass density, a lower NUE, and a higher NUX. And that means the flavor conversion is changing the flavors on the direction of NUE to NUX. And indeed, we can also see this in the neutrino luminosity evolutions. So here I'm showing you for the upper panel and lower panel, both neutrino luminosities, but upper panel is showing the absolute value, lower panel is showing the fractions over overall luminosities. So what we see is that with flavor conversion, in the top panel, for the no mixing case being blue, you have, compared to the other 3 mixing case, a lower NUX luminosity and a higher NUE bar luminosities. That means flavor conversion will give you higher NUX luminosity and lower NUE bar luminosities. And for the flavor fractions on the lower panel, what you see is the no mixing case on the very left, the other 2 mixing case on the right. And different colors represent different times in the simulation. And you move from blue to this yellow color means you have a flavor close to its equilibrium state. So what we see here is that the distribution of different flavors are drawn in different axes. We only have 3 axes. That's because we combine the mu and tau neutrinos and also the antiparticles together. And with that, we can then see this more clearly that if it's at the center of the domain, this diagram, that means you have an equipotential pattern. Indeed, with flavor conversion happening, you end up with more heavy lepton neutrinos, and that push your system to a more equipotential phase. Another interesting feature of luminosities of neutrinos is that it can be correlated with the emissions of gravitational waves. So here on the left plot, I'm showing you the peak luminosities for neutrinos versus gravitational waves. So the background points drawn in the gray color are simulations done by Crisinato in 2021. There you also have this linear correlation. And our models are drawn in different colors with different equation state. Basically what we see is that there are more interesting feature is with flavor conversion, you have even higher luminosities. So here for the DD213 and SFHO13 models, which you have high density regions undergoing flavor conversion, they sort of increase your peak luminosities for both gravitational waves and neutrinos. And the reason why that's happening is because with more neutrino mixing happen, we have a more compact remnants, and that can be shown on the right plot here. So we are showing the rho max, the maximum density at the center, and higher gravitational binding energy will be emitted as well. Another thing we can look at is the flavor conversion's impact on the ejecta. So ejecta, as what we discussed before, in previous study, they already found this change in the electron fractions. And we can also see this with this XZ diagram showing animations between 3 different models. So here I have no mixing versus 11 versus 13. The left one is no mixing, the other two are having flavor conversions. So what you see is that the electron fraction, basically if your electron over proton plus neutrons, is decreasing in the flavor conversion case. If that happens, as I'm writing down here, you have the reactions from nu e to n, nu e plus n to p plus electron being going the reverse direction. That means you have more neutrons. And that's why you have a smaller ye. The differences, as you can see, is also most prominent in or near equatorial plane. With the differences appear in ye, we should also expect something change in the nuclear synthesis. And here I'm showing you two plots. Left plot is the ye histogram. On the right, you have the relative abundances over different atomic number. So again, with the flavor conversion from the electron type to have lepton types, you basically reduce the neutrino reabsorption effect that boosts your neutrons. And if you have more neutrons, you have more neutron capturing, and then you increase your happy element band, which here is the lanthanide actinide bands that include gold, platinum, and so on and so forth. As what we quoted here, around 200% to 1,000%. So that's really order of magnitude differences. And more interestingly is this difference can exceed the reported 30% numerical uncertainties in comparing different numerical schemes. So really this is significant. Next thing that we find pretty interesting is this fast wave instability analysis. So we do this analysis by estimating this electron lepton number flux factor. When this quantity is larger or equal to 1, that means your region is unstable, so fast wave instability. And if this value is smaller than 1, that means it's stable. So here you see this red color representing unstable region and blue representing stable regions. So we're plotting this, also trying to animate this one with no mixing versus 2 mixing models from left to right. So you see that one of the very interesting feature is no matter if you have fluid mixing or not, you always ended up with some kind of instabilities. So this is really kind of intriguing because the fact that our subgrid model or flavor conversion model is to remove or at least mitigate this instability by introducing flavor conversion, and yet you still see this instability grow from time to time. That means there must be some kind of dynamical effects like advections or just the generation of instabilities by the global dynamics. So this is really something intriguing. Okay, time to summarize. So this is really the first BNS merger simulations with neutrino flavor conversions. And through this study, we found that neutrino flavor conversions can change the neutrino luminosity, the mean energies, and the flavor hierarchy. The flavor conversions can also give rise to a more neutron-rich dynamic ejecta and boost the heavy element productions by potentially order of magnitude. Neutrino flavor conversions can increase the remnant compactness, can change the neutrino and gravitational wave peak luminosities, and potentially also leave some imprints on the post-merger spectra. Some future work we can think about is first we can think about improvement for the neutrino modeling. There are already a lot of improvements on the modeling that people have proposed, and this is really an active field. Secondly, we can also think about, in the microphysics side, implementing muonic interactions to separate the mu and tau neutron treatments, and also think about pair processes and inelastic scattering. With that, I want to thank you all for taking your time to come to the session and hear my talk. I will see you in the discussion session.